Good morning, my name is Will Thompson. I'm the Director of Engineering for Privacy Dynamics. Today I'm going to give you a very fast overview of data privacy preserving methods through the lens of us developing the first version of our data privacy service. So Privacy Dynamics set out with the mission to be a privacy switch for the modern data stack. So we want to offer simple, robust privacy controls for modern data pipelines. And we started out, and our initial conversations with customers led us to focus on data sharing use cases. And so this is where a customer wants to take some data, hand it off to a third party safely, and then have them analyze the data. So what is data privacy? In this context, we're talking about a data release. And so this is separate from preventing access to data or tracking data access. So we are focused on the case where we're protecting identities in data when access has already been explicitly allowed. So some important concepts to cover here. The first step towards identity protection is to remove or replace direct identifiers in the data. And these are like names, addresses, and phone numbers. And so this is called pseudonymization. However, even though direct identifiers have been removed from the data set, combinations of quasi-identifiers, things like age, zip code, and gender can be used to re-identify people with high probabilities. This is called re-identification. Also, new information can be revealed without linking using inference attacks, as this is if you query a database multiple times to reveal new information. And so what we want to do is anonymize the data, also known as de-identification. And what we do is we change quasi-identifier values or personal attribute values, and this mitigates the risk that we are going to leak sensitive information about a person. And so another important concept is the privacy utility curve. And so what's happening here is we have to change data in order to protect identities. And so every method to protect privacy comes at the expense of some accuracy. And so the goal is to find the most acceptable trade-off for a specific use case. And so the first method we explored is global differential privacy. And differential privacy is defined as the indistinguishability of a computation's output when the input differs by one individual's data. And so what does this look like? We have a data set, we perform a computation, and then we get a result. And so then we take that data set, add one individual's data to it, perform the computation again, and get another result. And what we can say is the computation is differentially private if the output or if the results are roughly the same. And so we measure how roughly with epsilon, also known as a privacy parameter. And the closer epsilon is to 0, the more private we are. And then the larger epsilon, the more risk there is of leaking information. And so this is nice because it only adds noise to a single statistic. And so this leaves us with high utility. Differential privacy is unique in that it's a strong guarantee. And so this is an absolute worst case scenario on information loss. And so from this, we get some important properties. One of these is composability. So if you perform multiple computations on a data set and you have epsilon values for each and you want to know what the total information loss is if you release all those statistics, you can sum the epsilon values and that's your total information loss. And then in addition, you don't have to make any assumptions about what an attacker might already know and what they might be trying to get from you because this is already a worst case scenario. And so these are really valuable properties. But this didn't really fit our use case well. The way this works in practice is you have to have a centralized system that mediates the queries between the analyst and the data, and then the centralized system will return differentially private results to the analyst. And so analysts have to use a centralized system and instead of their own tools, and then also the centralized system requires an element of trust because it holds the unprotected data. And then ultimately, in order to protect the privacy, we have to set an epsilon value budget ahead of time. And this is, you set this budget and then analysts query against the budget and then there's a limit on what they can do. So this implies that you need to have some understanding of what queries you need ahead of time. And this doesn't really work well for a lot of data analysts who prefer to use exploratory analysis to understand their data. And so the next method we looked into is k-anonymity. And this is different from differential privacy. K-anonymity is a property of the data set, whereas differential privacy is a property of the algorithm and its output. And so a data set is considered k-anonymous if each record's quasi-identifiers match at least k-1 other records. So what does this look like? We have a handful of quasi-identifiers matching in a data set, and the equivalence classes have varying levels of matching, and we can see that there's one unique value. So this is a k-anonymity is similarly a worst case, and so in this case we have to say k equals 1 for here. So what we want to do is increase this k value, decrease the risk of re-identification, and so what we do is we want to generalize some values. And so here we will take the unique value here, this lion, and we will group them with the tiger, and then we can say they're all cats. And so now that unique row has been eliminated, and k equals 2. And so this is what it looks like in some real data. So here we have 2 unique rows, and then we can group those unique rows with other rows, and here you can see in the top row, in the top group, the age column has been generalized to a range, and in the second group, the zip code column has been generalized and the Hispanic column has been suppressed. And so now we've eliminated those unique rows. And so this is nice. It protects whole data sets, so data can easily be shared. It directly addresses linking attacks, and it's intuitive to think about. And then we also only have to modify the data that is at risk based on our threshold. And speaking of thresholds, k-anonymity is only a threshold metric. And so, so what that means is, this is an example. You have the same data set anonymized using 2 different functions. And you can look at the distribution of record level k-anonymity and see that it is different across these data sets despite the fact that the k-anonymity is 5 for both. And so these would have different real world risk. So we need more metrics to get a complete picture of what's going on. And so this is a little bit more complicated because it's based on the probability of a successful attack. So we have to consider what might an attacker know and what background information might they have. In addition, because it's probabilistic, this is a weaker guarantee than differential privacy, which is more of an absolute metric. And so it's a little squishier. And then k values aren't composable like epsilon. And one of the problems that we ran into is the algorithms that are used to generalize data are optimization algorithms. These tend to be quadratic or close to quadratic, so it's difficult to scale. And so this was difficult for us. And so that brings us to local differential privacy. And so local differential privacy follows the same definition of differential privacy as global, but it's applied to the whole data set. And so the classical example of this is called randomized response, and the concept is that you want to offer plausible deniability to a survey respondent when you're asking them for information on a sensitive topic. So the way this works in practice is essentially you flip a coin, and then depending on the results of the coin flip, the person will either answer truthfully, or you flip the coin again and then randomly enter yes or no. And so this method, it originated in the 60s, so it predates differential privacy by decades, but it still meets the definition of differential privacy, and we can use the formal definition to derive an epsilon value, which is approximately 1.1. And so this is a pretty good epsilon value, and then note that we get 50% noise in this data set in exchange for this epsilon value. And so that was an example for binary data. We can also do this with numerical data. And so this is how Apple handles sending histogram information to their systems from your devices. And so this is similar to the survey questionnaire. This is applied client side. What they do is they take the histogram value, it's encoded into a one-hot encoded vector, and then using this, this probability here, and epsilon is in the denominator here, we swap every single value in the vector on this probability, and then now we have produced a epsilon differentially private vector, and that goes to Apple. So this protects whole data sets like k-anonymity. That's nice, and it offers us strong privacy guarantees like and composable epsilon, like global differential privacy. But one of the difficulties here is that differential privacy protects something different from k-anonymity, which is designed to directly address linkage attacks. And so it's difficult to reconcile epsilon and re-identification risk. And the issue is that in practice, you can have a large epsilon, which would indicate poor privacy, but still have low risk. And so this is difficult if linkability is what you're interested in. And then the biggest problem for us is local differential privacy applies a lot of noise, orders of magnitude more noise than global typically. So then finally, we have synthetic data. And so this is, idea here is you train a neural network or some other machine learning model on unprotected data, and then you generate an entirely different data set. And so this seems like a pretty ideal way to protect identities. Like intuitively, you would think this is not personal information anymore. But in practice, this is not the case. Synthetic doesn't automatically mean private. It's still vulnerable to inference and linkage attacks. And so you still need to apply noise to synthetic data in order to protect it. And so once you've applied the noise, then the privacy utility trade-off doesn't really outperform any other methods. And because you're using this generative model, these models tend to be more inscrutable, and the privacy gain and utility loss can be very hard to predict. And so for that reason, it's just tricky to use this in practice. But, and then the model training phase is very expensive. On average, these algorithms are more expensive than k-anonymity. So we would have a lot of trouble scaling this. But there is some new work has been done on re-identification risk instead of differentially private assessments on this. And so there's potential for better utility, but when you're addressing re-ID risk for synthetic data, but this is some new work. We came away not really satisfied with any of these methods, and so we decided to pursue our own method and address some of these other problems based on k-anonymity. And after we worked on this for a while, we discovered that we had kind of reinvented something that mostly existed in the literature called microaggregation. And so microaggregation is similar to k-anonymity, but traditional k-anonymity is optimizing around a generalization hierarchy. And one of the problems we have is that it often results in overgeneralization if the hierarchy isn't fit for any specific data set. And also you end up mixing categorical data, these generalized values with the original values. So this makes it hard to compute downstream for analysis. And so what microaggregation does is we use cluster analysis instead of optimizing for a generalization hierarchy. And then in a second pass, we generalize the clustered values. And so we end up with higher precision because we're able to cluster around the closest values and then essentially publish the cluster's center. And so additionally, since clustering happens independently, in the first step, you can replace generalization entirely with an arbitrary aggregation function. And so we can publish a more accurate aggregate value using something like median or mode. And then at the same time, we're maintaining the semantics of the data to simplify downstream analysis. And then also, since we're using clustering, this opens up possibilities for increased precision around complex data types like geographical data. And in many cases where generalization would force you to suppress a value because you've reached the top of the generalization hierarchy, you can just publish the mode and still have more accurate data and avoid suppression entirely. So there are several other things that we had to address that I didn't have time to get into in this talk. So this was our process for implementing data privacy to fit some customer needs for our launch product. And the key takeaway here is that every use case is somewhat unique. And so I expect that we will need to add or augment our methods to address new use cases as they come up. And so the most appropriate methods for addressing privacy depend not only on the privacy utility trade-off, but also requirements for efficiency, usability, and data needs and trust. Thanks. I hope you found this talk helpful.